The last thing I'd like to address is how to calculate singular value decomposition. So how do we go from a matrix A to A equals U times sigma times V conjugate transpose? Well, we can do this with a few steps. Our first step will be to look at the Gramian of our matrix. Here's where a lot of what we've done in the course comes together. Remember that the Gramian of our matrix, A star times A, is a positive semi-definite matrix. So that has the same rank as A. So what we do is we order all of the positive eigenvalues of the Gramian, lambda 1, lambda 2, down to lambda r, accounting for algebraic multiplicity. So we can do this because A star A is a positive semi-definite matrix. The next thing we do is we use the spectral theorem to factor A star A as A star A equals V times D times V conjugate transpose. Here, D will be the diagonal matrix with the positive eigenvalues of A star A on the diagonal. And V, of course, will have orthonormal columns, which is guaranteed by the spectral theorem. So what we're finding here is that in singular value decomposition, the columns of V can be used in a spectral factorization of the Gramian of A. To finish finding SVD, we take sigma to be the square root of D, and we take U to be A times V times the inverse of sigma. What this is saying is that the singular values of a matrix are the square roots of the eigenvalues of the Gramian, and then we get our matrix U with the formula A times V times sigma inverse. Let's see this in an example. So I'm starting this example with a spectral factorization of the Gramian of a matrix. So here the matrix I'm studying is the 3x2 matrix, A here. I'm starting by taking the Gramian, A star times A, which is this matrix 2, 1, 1, 2. And then I went ahead and calculated a spectral factorization of this matrix. So here V is this 2x2 matrix. And what we're finding in this spectral factorization is that the eigenvalues of the Gramian are 3 and 1. Now what we do is we apply the formulas in our steps. Sigma, which has the singular values on the diagonal, is the square root of D. So we go and we take the square roots of the eigenvalues of the Gramian. We get square root of 3 and 1 on the diagonal of sigma. Then, to calculate U, we take A times V times the inverse of sigma. So sigma is easy to invert because it's a diagonal matrix with positive diagonal. So to invert sigma, we just invert the diagonal entries. By taking A times V times sigma inverse, we produce the matrix U in a singular value decomposition. And this finishes the singular value decomposition. A now is U times sigma times V conjugate transpose, where A is the matrix we started with, V is the matrix used to unitarily diagonalize the Gramian of A, sigma is the square root of D, so the singular values of A are the square roots of the eigenvalues of the Gramian of A, and then U is obtained with the formula A times V times the inverse of sigma. And that's it. That gives us our singular value decomposition. The hardest part is applying the spectral theorem to the Gramian of our matrix. After that, we need only take the square roots of the eigenvalues of the Gramian and apply a formula to get our matrix U.